for onboard AI application for satellites. This is a relatively new uh, program in JAXA, and I think this is the first time to present in public about this project. So it's really exciting to share, and also I'm happy to hear in person. I really love the keynotes. Yeah, so I wish if we had I can have a good feedback from this place. So the JAXA is located in several places in Japan, and I came from the near Tokyo facility. And um, I'm also I'm in R&D organization, and I'm belongs in software engineering team. And we have several teams in this team, and I'm responsible for software architecture. And as a theme of our architecture team, we like to have a software architecture for more flexibility for application and wide open to everyone. And this everyone means that I think we got the presentation from Caltech yesterday, and um, the number of the flight software engineer, and Japan has serious problem about the number of flight software engineer, and um, they call like endangered species in Japan. Yeah, there's so we need to pull the software engineer from the other domains. So we would like to open to everyone to to get into the space domain. So that is our priority. So as a motivation, not in space domain but generic large software systems. It is said that it's difficult to determine the actual application requirement before they release, but they release in the beta and they get feedback for feedback from the user, and then they determine the requirement. And if we connect to like multiple edge computer or microservice, it requires a quick improvement to optimize as a whole system because they create their application or they create their subsystem individually and get together. So they need to quick improve and quick change for it. To do to do that kind of stuff, the DevOps practice to are taken and shortened to development life cycle and do continuous modification or improvement. So I think the space software, flight software are getting so complex in these days. So same thing can be said in modern satellite service as well. So I'd like to talk about a conventional satellite flight software. I don't know about the other. uh, I don't know about other parties, but this has happened in JAXA. Um, um, all flight software are developed monolithically and strongly depends on hardware. We need to set a static stuff, and also it's really difficult to make a major software change on our orbit about and all of stuff. But I think it's ridiculous to think about this kind of stuff in all software. It is indeed that some software should be developed rigorously, completely before the launch or operation. But some software can be. I think some software can be more flexibility, like about like payload mission app can be more flexibility. So um, some soft So I think that some flight software should accept a quick on-orbit major change to meet the user demand. So we would like to have the software framework or architecture to accept the major change on orbit. So this is what JAXA thinking that we need to change the service architecture of satellite service. Um, the conventional satellite service is kind of static thing. We collect the user demand to uh, to bring up the new project, and the user need to wait about like average 5 years to get the result after they they put the demands for the satellite service. And the 5 years is quite long term, so the user demand will be changing that period, they but the change cannot be accepted in the time. So we don't want to do those kind of stuff, but we want to um, we want to treat the dynamic user demand like about a weeks of the demand. I want to do those kind of stuff and get in tune in the weeks, or uh, we want to give the service like in a 3 month is like 3 months lead time, even if it is long. So and also we want to change the configuration of satellite service architecture if we cannot meet the user demand in current capability, like adding one more small satellite and expand the capability of satellite service, and we want to do those kind of stuff. So to do this stuff, we think that it's really important to make make a capability to change the application in on orbit. So in this time, we select the container architecture, which using Docker stuff, and we want to have a capability to achieve the changeability to service application. So um, application developer will develop their app with using a container like Docker container, and it contain the Docker contained container, and they only need to develop the specific application layer, which in orange part in this figure, and it's deploy only the specific layer to the onboard computer and satellite, and it and get together with the base image and run into the payload OBC. So this is the kind of stuff that we want to do. And I think most of people knows about the container Docker stuff, but I'd like to quick explain about it. Container is a unit of software which packed code in its dependency in its environment, and it runs an app virtually with relatively low computational cost, like compared to Hyper-V approach. And I like to highlight that it's really increased the portability of application. Like we when we we create the really simple convolutional neural network application in our environment, uh, and deploy to the target app natively will take like adjusting work to the target hardware will be like take 8 hour cost for me. But when we use a container and just put in the container and make it run to the make it run in a target hardware will just take the 20 minutes. And this is really I think this is really advantage for the to introducing the container stuff in the onboard software. But absolutely, there's a pro and cons of this container stuff. Pros is, as I mentioned, is lower the hardware dependency, and as apps can be developed without target hardware, so we can introduce to we can having a lot of person to be developed this kind of application, and it's really generic techniques. A person who belongs to software engineer stuff knows uh, knows about this. So we can call a lot of person. So the person person engaged with software engineer um, can comment can come in to use this technique. So the learning curve will be really, you know, a- will be low cost. But we have a lot of cons for this container stuff. It still requires the computational costs, the native apps. Like we should run this application virtually. So onboard computer need computational costs. And the container comes from the cloud computing techniques. So they are expecting the scale of computational resources, but we can do we cannot do it in onboard computer now. And it has the overhead for the visual virtualization, and it also it's increased the complexity of the onboard computer. So there will be the cons. And I would like to also add that there's no time guarantee in containerized applications. So we cannot do the sensitive like milsec order control stuff. So this is so we need to select the application in this period. So we have a little experiment about to check the how much overhead of the virtualization of, of how much overhead of virtualization will come as the onboard flight software. And we confirm the performance of AI application which develops as a container app. And we prepare two app like in here. One is a Max RC, and then this is the application for object detection, which detect maritime vessel detection, maritime vessel. And as we know, the Max RCNet is not for edge computing model, but we are setting this example for the worst case one. And the second one, we prepare the YOLO V7 tiny model application. It also detects the um, maritime vessel, but image size is different from the Mass RCNN one. And this is the model which we can use in the edge computer stuff. So this is the normal application which we are expecting in our project. And we implement this in Python and C and C++. And I think we have a lot of discussion about the language for the onboard computer, onboard softwares. But container, you can just pack in them and just run in it. So we can select the language which we want. So well, that is the advantage of container app, I think. And this is the target hardware of our experiment. We use a processor with AMD, and we use operating system for Ubuntu, and we are thinking to launch this kind of onboard computer in near future. And we are expecting this onboard computer as a payload edge computer. Okay. And about this slide, the message of the slide is we are using the app which works in this experiment. These apps are created with Docker container in 2 or 3 days, including the training, including the time to train the model. And I think the model can be more little if we optimize, and also we can higher the accuracy of the um, pro- accuracy performance. But we just packed in 2 or 3 days, and we are expecting to develop apps in like in that time period, like one or 2 days. We don't want to take years to develop the application. So this is expectation that we are want to do it. And this is the result of process performance. Um, the upper result is a performance that addresses a single image to detect a vessel. And I'd like to highlight that to check about the overhead of virtual running the application virtually. We want to compare the non-container performance and container performance between a uh, non-container application and container application, a mask RCNN. Um, Non-container, which implemented natively, it takes a lot of time, and it takes a lot of time to implement with non-container, but the process time is like 2.8 seconds uh, by process in only the CPU. And if we use a container to run same app with the non-container version, it will take 8.3 seconds to process. So we can observe that there's some kind of bad effect by using the Docker runtime and those kind of stuff. And also there are remarkable bad effect, not a good effect from the image load time. We need to load container image before it runs, so it takes 38.4 seconds for it. So, um, and this is the worst case. So, but we can observe that it's really hard to use. We need to select the occasion to use this kind of container app if we have such long load time. And also, this is the we want to point out about the YOLO V7 tiny model. This is the one. This is the one we are thinking we want to pack in our onboard computer. Image load time will be 1 second. This is I don't know, but it's kind of acceptable. And process time is like 4 seconds. And I don't know. This will meet the user demand, but we think that we need to figure out how we should handle this application with this process time. And a specific layer that we need to deploy to onboard computer will be about 25 megabytes. And we need to carefully reduce the size of the image since we can only upload, the upload capability and resources really limited. So, but we think that this 25 megabyte is acceptable in for now. So we are pretty satisfied in this result. And I like to show the peak power of this when we run this application. Um, it's about we are using that we are connecting to the monitor, so we have this kind of power consumption which we are not going to use in orbit, but it's around the 30 watt. And I think this is really limitation to use these kind of onboard computer in a small set. And this is just for information. This is the result of the running YOLO V7 tiny model to run a 10 time and detecting 100 image in each process. And, and it's showing the CPU temperature and also the CPU utilization. And I want to point out that the control of the CPU allocation works well. And these results will, I don't know, this we are not sure that this result is good or bad, but we would like to make this result to be the benchmark, the starting point benchmark to evaluate like other apps or other target app or other target hardware. So I'd like to wrap up the presentation. We show the performance of the software framework to accept the major change on orbit with container techniques. And we found that we need the careful resource management, though we found that the capability is good enough to pack it in as an on board. And we are planning to have a demonstration of this kind of framework and we'll launch in 2024. And we have a 1 year period experiment for it. And the experiment with the container apps like packing AI apps are planned to be wide open to all. We are planning to do hackathon in this fall, and everyone is welcome to join our experiment. So if you're interested in this demonstration, please contact me. Please ask me. I'm in person here, so it would be appreciated to with discuss with me. And I'd like to thank to all of my team, which carrying this experiment and for and this project. So thank you.
Okay, we have a couple of questions online. First, Ben Bornstein asks, I'm a little naive when it comes to deep technical details of containers. What robustness and reliability guarantees do containers offer for the rest of the system? For example, can you prove an errant container cannot adversely impact or even take down the rest of the system?
Great questions. Yeah, the reliability part is one of concerns, and um, um, it's dependent. So it has a kind of reliability, but we need to check. We need to further check about it.
Okay. All right, and let's go in the room over here.
Hi, thank you. Between the three approaches, the yellow container, the masked RCDN with the container, and the native, which of the three were, in your opinion, the easiest to implement?
Good questions. Um, I think it just depends on what we want in from the model. If we if we get I think this like kind of CNN model is really easy for the entry level, but I think that is a common sense in here. But even if it's um, easy to implement it, but if we cannot get the certain accuracy from that model, it will take nothing. So I think it depends on the task that want to do. But my answer is that starting from CNN will be really reasonable.
Okay, thank you.
Thank you.
Okay, and just in the interest of time, we'll try for one more online and then one more in the room. My apologies for that. Okay, so Tim Bird asks, do you know what extra software packages are required in your Linux distribution to support deployment in Dockerized containers? Presumably the Docker system itself, and also what is the storage footprint of the container system?
Oh, really good question. um, uh, um, it's so detailed. So um,
One, yeah, and one option here might be to hop on the thread after your presentation and answer some of the online questions. The question is, do you know what extra software packages are required, and what are the size of what's the size of the container, or is it swamped by the size of the application within the container?
yeah, I need to check it. And I write in this. I write down in this chart that we are not using the original Docker, but we are using the kind of modified Docker stuff. So it's required the special package for it, but we can also handle in the original Docker, which really generic ones. So I reply to the Slack in after this.
Okay, and one last in the room. Go ahead.
Hopefully a short question. I was just curious what you're using to run the neural networks. Are you using TensorFlow or PyTorch in the container or something else?
Oh, thank you for your question. We are using generic library like TensorFlow and PyTorch and those kind of stuff.
Okay, thank you.
All right, thank you. Let's thank Naoko.
Thank you so much.